Hello? Okay. Yeah, but let's start for the motivation. So the whole motivation for my work began with the same probably as many of you. So the Fukushima Daiichi power plant nuclear disaster. And I think that what you all envisioned at the time is that we wanted robots to be able to sort of get in there and interact with the environment in a way that was not realistic at a time for the machines to do. So I think it was a big wake-up call for the robotics community to figure out, okay, we really need to think about this problem. Um, and many of us that are here in teleoperation of robots also thought, okay, maybe the humans can help, right? So what if you can, capture human whole body motion, send that to the robot's gonna be interacting with the environment, and then you get yourself a robotic responder. And in fact, humans are really good at controlling machines. So this is a drone being teleoperated by a human teleoperator, and you can see he's able to fly in this very complex scenario with doing very dynamic maneuvers, and probably in a bandwidth that he's not aware that he's doing. So practice of the operator also plays a huge role in how well the system can be controlled, right? And actually, this is actually one of my favorite parts. Yeah, so it's crazy what humans can do when they actually get to practice with the system. So why don't we do the same thing with, for example, sending a robotic disaster responser? Well, there's a fundamental difference between flying a drone around and actually interacting in the environment. So let me give you an example. So let's say you're a firefighter and you want to put down this door using an axe. You're not going to just swing your arms and hit it. The strategy is this whole body strategy that plays a huge role with the force that you're applying, but also the feedback from an environment. Right, so the feedback that you get from doing this sort of task is very important to be able to do the test right. So if the door opens or if the door is locked, your reaction to the behavior is going to be different, right? And this is not something that just firefighters can do. Everybody does this all the time. So let's see, for example, this little girl, she's trying to open a door that's too heavy for her, right? And what she does is actually go into this unstable condition and lean against the door so she can amplify the forces that she's able to exert and actually open the door and move out. Right? So I think there's something we're sort of missing here when you try to do this whole body teleoperation strategies, right? So let me try to convince you on my way of thinking about it. So I think it should begin the same way. We should get a human operator, and we're being controlled by this sort of black box controller here that we don't know exactly how he works, and you're going to command the robot to move and exert some sort of force on the environment. The environment is going to respond to the robot with forces and some other feedback, and something that I think we're missing here in the whole body level is how do you close the gap? How do you give the human the sort of feedback in order to really leverage human motor intelligence to control a robot to physically interact with an environment, right? It's not more on the kinematic level anymore. So given this way of thinking, this is my hypothesis. I think that in the whole body level, if you can map the motion of the human to the robot in a correct way, and if we can provide to the operator the correct physical feedback, the idea is that we can really use this human whole body coordination and motor intelligence to control these machines, right? So I really do believe that providing the correct feedback is a very important aspect of this. So throughout this talk, I want to try to convince you of my way of doing this. So first, I would like to just briefly talk about the HERMES system, which is a system that I worked a long time ago. Next, I'm going to talk a little bit about the human-machine interface that we developed for high-speed teleoperation, which is necessary, and also whole body feedback. I'm going to present you the bilateral feedback strategy that we developed for synchronizing locomotion, and I'm going to present how to control two systems using that. One is going to be a simplified cartridge pull, and the other one's going to be actually the robot itself, okay? So let's get into the first one. So let's talk a little bit about the HERMES system. So the HERMES system, it's a system that we developed back in 2014. And just now we managed to get this really cool picture from IEEE. They just released the article super late now about it, but it's still relevant. I still think that we did some really interesting things back then. So in order to map the motion from human to robot, we did the simplest idea, right? So we did the very simple Cartesian mapping. So the human Cartesian position of the arm would be mapped to the robot scaled by the arm length, and also the position of the body of the robot, the body of the operator would be mapped to the robot to copy its posture, right? And you can see that the human operator will also wear that whole body feedback suit that later on I'm going to explain how it plays a role into the whole thing. And what is nice is that because it's a teleoperated system, there's a lot of stuff you get for free, right? So human dexterity, if you do it right, you can achieve these very interesting behaviors, which is for an autonomous robot is incredibly difficult to do. But also, we try to do some more interesting things. So we also use a robot to put out this mock-up fire just to sort of illustrate the potential of what we're trying to achieve. This was actually a demo that we did for a Robotics for Good video. But yeah, so it was just for shows. But the robot itself, we never designed HERMES to work in this semi-static regime. So what we try to do is actually go into more dynamic situations. So probably some of you are familiar with this video. We try to actually teleoperate the robot, for example, to break through the drywall. And we're just trying to demonstrate that you also have to design your robot system correctly such that it's able to absorb these impacts and also produce large forces using whole body coordination, right? And because it's a simulated, teleoperated system, we also use to do more interesting things. So such, for example, grabbing this firefighter axe and try to, hit this mock-up door using human command. So this is the vision that you see from the operator point of view. So we learned that actually if you make the robot leans against a strike and just halfway through hit it, it would actually be way more effective. Because first we're just trying to blindly swing the arms and the robot would just be torqued back. Right? And because you have the teleoperator there, we can just try all these things on the fly. Right? Okay, so this is how we mapped human motion to the robot. So how did you close the feedback? Honestly, at the beginning, you had no idea how to do this. So we didn't know exactly what sort of forces would be appropriate for the human to experience while the robot is doing its own activities. So the first thing that we tried was very basic, was a quasi-static notion of stability. So we took the load cells on the robot, and if you project the support polygon, there's a point on the ground that's called the COP, right? I think most of you are familiar with this. So the first thing that we try is, okay, let's apply a force to the operator that is the inverse of that distance. So the closest the COP is from the edge of support, the harder the force that you apply back, right? And I know this is a very naive approach, but it was the first idea was let's try to get a sense of what we can do with this. And we got some interesting results. So for the robot, if the robot's standing there and the person is trying to maintain a posture, if the robot gets hit, then you can feel that. If the robot is trying to work with this sort of payload, then the operator can kind of come up with a different posture in order to regain balance of the robot. So this was all very interesting behaviors, but it was very basic, right? It was definitely not a complete story. And there's something else that you need to do if you want to really go into a more interesting regime for these machines. Okay, so we learned a lot of stuff. We learned how to teleoperate very fast motions. We learned how to do large feedback forces, which is very complicated if you're trying to make a very transparent system. And also learn how to design these humanoid machines such that they could take these impacts to the environment and it would be robust enough to do that. But if you're a humanoid and you're not attached to the world, then if you want to apply large forces to the environment, you also need to balance and regulate foot placement, right? So the feedback applied to the person needs to take into account some sort of locomotion dynamics as well, right? So my research is about that. So how do you build up all the strategies in order, for example, to come up with more interesting behaviors, such as taking steps, build up momentum, and then hitting the wall with the firefighter axe, which is sort of what we see the little girl doing, right? She was sort of losing stability for a second in order to amplify the forces she was able to apply. And that's the sort of behavior I want to explore. I don't want to restrain the robot to be in a safe condition. I wanted to have an experienced operator to be able to really understand how to control this machine, these added dynamics, right? Okay, but how do we do this? So let me talk a little bit about the human-machine interface that we developed in the lab. So this is called the BFI, the Balanced Feedback Interface. It's an old name. We don't go by that anymore. But this is sort of the idea. The person wears this vest that is attached to a fixed frame using these push and pull rods. And these push and pull rods can apply a force on that line. So by modulating the force on the two rods, you sort of can modulate what are the forces that the person feels. So some sort of momentum or linear force. We track the foot position using this passive linkage system. And we did this because we can really push the sampling rate of the system. We can get something on the order of 10 kilohertz of sampling rate of the human position, right? We have a real-time computer that measures the whole thing. And also the person is standing on this 6-axis force plate. And that's going to be very important to understand the forces that a person is applying on the ground as he or she moves. But locomotion is a very complicated thing, right? I think all of us know that at this point. But so let me show you how do we break this down. So this is a very basic motion. You have the operator here stepping side to side. And what we do, we just care about the core components of that locomotion. So if you, for example, take the position of the torso, this is what I assume to be the central mass, position of the feet, and also position of the central pressure and then ground direction forces. This is kind of motion composition that you get. And that's what actually is the essence of locomotion. What is the interplay between your COP and what is the interplay between the central mass, right? So that's what I want to transfer to the robot. I don't care what the rest of the system is doing. But in order to do this, my first approach is to start slow, right? So let's try to reduce that to what most of you know as inverted pendulum. So if you isolate the central mass and the COP, you got a system that looks like that, which is pretty much a pendulum that there's a very popular, you probably all know about the system that's called a linear inverted pendulum, which is incredibly powerful. You would be surprised. So that's going to be very important to understand the strategy behind what I'm trying to do, right? So let me talk a little bit about the bilateral feedback strategy that I developed. So this is the pendulum, the linear inverted pendulum equations. If you consider the height to be approximately constant, and so the natural frequency of the pendulum is sort of fixed, you can write down an equation of motion. It's something very simple. I think all of you are tired of hearing this. But what is interesting is that if you do the mode decomposition, you get a system that's first order that looks like that. And you got two states, actually. One of them is a state that's associated with the unstable pole. The stable pole, which is called the convergent component motion, that looks like this, is an augmented central mass state. And the second one is a state that is associated with the unstable component of the system. And this is the divergent component motion, or capture point, or extrapolated central mass, and many other names, right? So the idea is that we assume that the human is trying to control this unstable component, and is using the ground direction force in order to do that. So if the robot follows what the human is doing with the stable component and follows a scaled version of the inputs, then they should move in a similar way, right? So that's what I tried to do. And the DCM is just a projection forward of what the central mass is doing. So this is the key what I'm doing. This is a very basic principle of what I'm trying to do. So what we want is, if you have the human operator and the robot, what I want is to both systems to follow a kinematically similar DCM trajectory, right? So if the human is able to stabilize its own DCM, the robot is going to do the same thing. And in order to achieve that, I'm going to use feedback to guarantee that the time rate of change of the DCM is the same, normalized by the natural frequency, because the pendulum sort of relies a lot on its dynamics, right? And an interesting thing is that if you take this equation and you plug in the equation of motion of the entire system, you get two terms. The first terms, you got two terms. The first terms say, how do you scale the human forces such that the robot applies and it can reproduce that DCM trajectory? And the second term is, what are the forces that you should apply to the operator in order to make sure that this is guaranteed at all the time, right? So what I'm doing is actually I'm using feedback in order to synchronize two systems that have different natural frequencies, right? The idea is very, very simple. And what is nice is that you show that if you have this and you have that, the two systems actually show the same relative position of the central pressure, which is important because you want to be taking steps together, right? So the two systems become synchronized. So in order to demonstrate what I'm trying to do, I actually build the simplest system you can think of, which is the pendulum itself. So let me show you how to apply this to that simplified system. So if you remember, the human motion when it takes steps looks a little bit like that. This is the central mass, that's central pressure. And for those of you who have a more of a controls-oriented background, this looks a lot like the cart pole system, right? And the cart pole system is pretty much an inverted pendulum with a passive hinge on a rail. And the only thing you can do is place the position of this pole here, of this cart here, and in that way you balance the pendulum, right? So it's very similar to what we're trying to what I'm interpreting the humans trying to do when the person walks around and tries to manipulate central mass. So you cannot see here, but if you assume that the position of the cart pole is equivalent to the position of the central pressure, and the position of the mass is equivalent to the position of the human center of mass. So the systems are very, very similar. So we can actually teleoperate this, right? So this is a very simplified teleoperation scheme that what I tried to do. So you have the human operator, and as you move, you're going to produce some sort of central mass, DCM, and central pressure trajectory. We scale that to a scale that makes sense for the robot to follow, so according to the robot's dimensions. And then you're going to plug that in as a reference for some controller of the robot to follow. So in this case, I just use a simple LQR, but this can be your favorite controller you can use whatever controller you want. It can be anything of this sort. In this case, I just use a LQR. But a key thing here is the feedback force is actually going to compare the normalized velocity difference between the two and going to create a feedback force that's proportional to that velocity. So pretty much if the pendulum is falling faster, the human machine interface is going to push you faster. If the pendulum is lagging behind, the human machine interface is going to create drag and try to slow you down. So you try to really synchronize the two systems. So what happens actually is that when you put that on the real system, this is the kind of behavior that you get. So what I want you to look at is the position of the central mass, kind of equivalent to the position of the pendulum mass, and the COP also matches the position of the cart. So as you go in double support, kind of the base of the cart moves side to side, and it kind of copies what's happening. And this is happening despite the fact that this pendulum is about half human height. So what's interesting is that the person is teleoperating in real time a system that has different dynamics, right? So the person is able to generate this trajectories in real time despite the fact that the two systems have different dynamics. And this is done because there's a feedback force that's applied to the person, and I think you can see that later on when there's someone that pokes into the pendulum. Just a little bit. Yeah, so you're going to now. So you see there's a feedback force that's applied, right? So let me show what the states that we care are actually doing. So on the top, you see the position of the central pressure of the person and also the normalized position of the cart as you move. And on the bottom is this position of the human DCM and the position of the robot DCM as the two systems are moving. And the interesting thing is that they are synchronized despite the fact that the pendulum is shorter than the person. And if you look at the feedback forces, this is what they look like. So in blue, these are the horizontal forces that the person apply on their own central mass as he moves. And in red, that's the feedback force applied to the person. So in this case, because the pendulum is faster, the feedback force tries to accelerate what the person is trying to do. So it is in phase with what the person is trying to, the sort of the forces the person is trying to produce. Right? So that's interesting, but we don't want to teleoperate pendulums, right? We want to apply to the actual robot. So let me give an example of how we can do that. So next, let me show you how to apply that to an actual bipedal robot. So in order to do this, I created this robot. It's called Little Hermes, just because it's really small. It's about 30 centimeters tall and only 6 kilos. And in order to accomplish what I was trying to do, there's some design features that I must point out. The first one is that it uses what we call proprioceptive actuators, which is a whole other topic, but it's the same actuator that you guys see on, for example, in the Mini Cheetah, if you guys are familiar with this. The legs are very lightweight. The transmission is as efficient as I can make. The feet has this force sensor that I just use as a contact switch, so if the robot knows if it's touching the ground or not. But I do not use a force sensor for force control. Force control is all done by the motor current and like kinematics. The robot has an IMU, real-time computer, LiPo battery, and this lightweight frame that holds encases everything. And unless I mention later on, all the experience I'm going to show the robot is going to be attached to a boom. So what I care is about the robot frontal plane. The robots cannot fold back and forwards. And I just want to point out that the robot is actually very, very small. Right? So that's what is interesting. So let me show some of the primitives that the robot must have in order to accomplish what I'm trying to do. So the robot is highly backdrivable. So this is with the robot off. And we want that because the robot needs to be able to experience impacts. And also, we need a high efficiency transmission in order to control torque at high bandwidth. And because it's so backdrivable, it can control force pretty well. So if you tell the robot, for example, to jump, it can produce a sort of very compliant behaviors with any sort of spring or force sensors anywhere. Right? And this is sort of the the base behavior that we require. But the robot also, the robot's not a pendulum, right? So it needs to have some sort of intelligence in order to translate the pendulum reference to an actual lag forces and the feet trajectories. So this is what the basic behaviors are. So when the robot's standing, it is going to calculate what is the right and left ground direction forces, such that the net force applied to the central mass is the summation of the component scale from human motion, so the human reference, plus a force that it tries to account for the error in the DCM, right? So it's just trying to, given the current position, it does a force distribution in order to stay at a certain, with the DCM in a certain position. So in this case, there's no operator. The robot is just trying to maintain the DCM in between the 2 feet. The second behavior, the second motion controller primitive that the robot has is to trying to control the feet. So whenever the person goes into a single support, the robot tries to track the operator's foot. So in this case, there's no operator. The robot is just trying to stay at a certain span, right? But it knows how to place its feet following a reference. In this case, the reference is just staying in pose. So these are the 2 basic controller primitives that we need in order to apply the strategy that I'm trying to use right now. So let's go to it. The first thing that we do is actually we capture this human motion. So this is the human moving around, the ground direction force, position of central mass, and all that. We condense that information to the linear inverted pendulum. And what we want is that the robot to follow that reference. So we scale the linear inverted pendulum motion to the robot size. And then we take that reference, and then the robot calculates what should be the ground direction forces in order to reproduce that, right? So the thing that I'm trying to achieve is that because locomotion is such a complicated system, what I want is the 2 simplified models to be dynamically similar. And if they are dynamically similar, the human can control this sort of dynamic trajectories in real time. And in order to make sure that these 2 systems are dynamically similar, what I use is feedback, right? So every time as the person moves around, there's a force feedback that's applied to the operator, excuse me, and the force looks like that, just to make sure that the 2 systems are synchronized. So just to represent what that means, if the robot is just standing there and gets hit, there's a jolt of force that's applied to the person that's proportional to the difference in velocities, right? And an interesting thing you can do with this is that now the system becomes, so if the 2 systems are synchronized, what you can do now is you can take simultaneous step. So in this case, the human just teleoperating the robot to take step at the same time. And this is what I think is actually powerful about this approach, right? So in this top plot here, that's the human DCM in blue and the robot DCM in red. It's noisy because the foot that I use is a little bit springy, so every time it steps, it shakes a little bit, so I'm trying to get rid of that. But the interesting part is that the COP of the 2 systems is actually completely synchronized. And the beauty of this is that now you can really control the robot to take steps together with you at the point that you want with a certain dynamic, right? So the points in magenta is on when the robot is on right support, and the human is on right support, and the points where it's in green is when there's left support, right? So this is what's interesting about this whole approach. But because you have a human there, you're not just limited by that. If you have a certain experience with the system, now you can start doing more interesting things. So for example, I show you guys how to do the synchronized steps, but you can, for example, also go into this more dynamic jumps, right? So if you modulate the ground direction force and you scale that to what the robot should be applying, now the human can control the robot to do this sort of jumps as well, which I think is very interesting. And the last thing is the robot doesn't need to be limited by what the human is experiencing, right? So if you have the right amount of autonomy, and I think being autonomous is a very powerful thing, and it can collaborate, you can, for example, control the robot to deal with objects that the operator is not looking at. So if the robot can deal with an obstacle and still make sure that the linear inverted pendulum, for example, is dynamically similar to what the operator is doing, then the teleoperation is still the same, right? As long as the robot has this sort of embedded intelligence. So I think that at some point down the line, what I want to do is give a little bit more intelligence to the robot, but follow the baseline trajectory of what the human is trying to accomplish, right? Okay, so after I did all this, I wanted to show how we could, for example, extend this for some sort of locomotion behavior, right? So the last thing I did was So, okay, if you have, for example, the human operator stepping in place and, for example, leaning against some sort of string, you can measure this ground direction forces and tell the robot to apply a scaled version of that. And if the robot does that while it takes steps in place, then it starts walking, right? So this is a very basic behavior. I just wanted to show that this sort of strategy has the potential also to control locomotion. So it can, for example, apply, the operator can step in place and then turn, step in place and jump, and you can start to get into much more complicated behaviors to do this sort of strategy. And this is what I want to try to explore, right? I think that the person being able to learn how to cope with this added dynamic is a very powerful strategy. Okay, so I did all these things. Let me just give you some words on my future work and research vision. So where do you go from here? I think there's a lot to be done. I think that improving autonomous controllers on the robot has a huge potential. I think that a lot of people ask me about learn. So sure, the robot can learn how to move better from human input. But I think that human practice plays a huge role. What I want to put as a specialist to control this robot, and I want to shoot for performance instead of trying to get to something that anybody can use. But also, how can you make the human-machine interface more immersive? But just giving the right tools to the operator, not trying literally to transfer the human body to the robot. And finally, how can the robot anticipate? So sometimes if you want to do some very fast stepping, so how can the robot kind of anticipate what the human wants to step and place its foot, right? So my next steps of what I want to do is actually combine everything that I did with HERMES, with this whole body manipulation, with the locomotion that I start to develop with HERMES, and I really want to look into tasks that involve this whole body coordination. So tasks that are highly dynamic, they involve balancing and foot placement, but importantly, how do you create large forces given that if you have a high central mass and you need to control your feet around, and you can design machines that can deal with impact. So these are all the things that I care. And the last thing I want to say is, you cannot see here, but a quote from my great masters, the greatest teacher failure is. I'm going to leave you with some of my failures because it's incredibly complicated task to do. And I'll take any questions if you have any. Thank you.